Yeah, welcome back to Laplace transformation part 6. Today we will study the Laplace of Heaviside function or unit step function, pulse function, second shifting theorem and Dirac-Delta function. This is very important lecture in point of competitive exams, application point of view and better understanding of application of Laplace transformation. So let's start. A very important lecture. Heaviside function. The notation of Heaviside function ht and ht defined as ht equals to 0 when t less than 0. It is 1 when t greater than equal to 0. Means at t equal to 0, we have a jump discontinuity. So this is suppose ft or ht function. This is t equal to 0. When t is greater than 0, the value of this function is 1. But when t less than 0, when t less than 0, the value of the function is 0. This is the value 0. At t equal to 0, this is jumping at 1. So I am making a small circle here because it is jumping at 1 at t equal to 0. So this is your Heaviside function. This function is also called unit step function. ht is also called unit step function and denoted by unit step function is denoted by ut. Unit step function is denoted by ut. So here ht is equal to ut equal to 0 t less than 0, 1 t greater than 0, and t equal to 0 is point of discontinuity. Some people also represent like this ut suffix 0. 0 is telling the point of discontinuity. So let's shift our discontinuity from origin to another point. Means if jump discontinuity is not at t equal to 0, it is on any arbitrary point t equal to a. If jump discontinuity is at the point t equal to a, then we define Heaviside function as ht minus a or unit step function ut minus a, or another notation is uat. A is telling the point of discontinuity. And its definition is it is 0 when t less than a, it is 1 when t is greater than or equal. So if we draw the graph for this up to t equal to a, the value of the function is 0, and from a onwards the value of the function is 1. The value of the function is 1. But up to t equal to a, the value of the function is 0. The value of the function is 0. So this is the 0 value. But at t equal to a, it is jumping at 1. So it has jump discontinuity at t equal to a. If put a equal to 0, then it becomes the previous case I have studied, the jump discontinuity at t equal to a. So this is the definition of Heaviside function, and I'm representing ft. Ft can be ht minus a or ut minus a or uat. Same representation. Means Heaviside function is also called unit step function here. Let's see some examples. Example 1 I am taking here. Represent in the terms of Heaviside function. f1t is equal to sine t into u pi t. So if we see, this is your unit step function u pi t, and this point is telling it is a point of discontinuity. Point of discontinuity. So what is the point of discontinuity here? T equal to pi. Means what will be the breaking of this unit step function? When t less than pi, the value of the function is 0. When t greater than equal to pi, the value of this function is 1. So if we multiply u pi t in sin t, you will get f1t. So f1t will become, this function is breaking at t equal to pi because pi is a point of discontinuity. We have compared it from UAT. I have told you the notation previously. UAT is the point of discontinuity. So when t less than pi, u pi t is 0. So the product will be 0 into sin t will be 0. When t greater than equal to pi, this value is 1. 1 into sin t will become sin t. So this is the use of Heaviside function here. We can break in interval also. For the second example, we have one more example. We can see f2t is equal to t square u2t. So I hope now you understand what will be the point of discontinuity. This is the point of discontinuity. T is equal to t is the point of discontinuity. So the function will break at t equal to 2. So t less than 2, t greater than equal to. When t less than 2, this value is 0. So 0 into t square will become 0. When t greater than 2, its value is 1. So it will become t square. So this is the breaking of this function. If we see the graph of this function, this is your t, this is your f2t. T equal to 2 is the point of discontinuity. T equal to 2 is the point of discontinuity. Up to t equal to 2, the value of the function is 0. Up to t equal to 2, the value of the function is 0. But at t equal to 2, the function is jumping. This is the graph up to t equal to 2, t less than 2. But at t equal to 2, at t equal to 2, if you put t equal to 2, the value will be 4. So the value is 4, and this is a look like a parabola. So this is the graph of y equal to x square type graph. So this is the graph of this function. Let's see next function, that is pulse function. It can be also defined with the help of unit step function. So what is the pulse function? We define a pulse function as, if a less than b, I am taking a less than b, f3t, this is I am representing a pulse function, is equal to uat minus ubt. It is a difference of two unit step function, a and b. A is a point of discontinuity and b is another point of discontinuity. I am taking a less than b. So what will be the definition of impulse function? Let's see the graph of UAT and UBT, then we will subtract. I am drawing the graph of UAT here. So t equal to a is a point of discontinuity here. This is your UAT. A is less than b, obviously b will be here. I am taking a is the point of discontinuity here. So remember, up to t equal to a, the value of the function is 0. 1 equal to a, the value of the function goes to 1. So this is the graph of UAT. Now if we draw the graph of UBT, in the UBT, the B is point of discontinuity, and up to B, the value of the function is 0, and from B onwards, the value of the function will be 1. So if we draw the graph of this function also, we can see that this look like this function. And it is jumping at B, and the value of the function is 1 here. The value of the function is 1 here. Now see carefully. A is here only. A is here only. It means between A to B the value is 0 also because A is less than B. Now if you subtract these values, you will get 3 cases here. What will be the 3 cases? T less than A because A is less than B. T is greater than equal to A but less than B when T is greater than equal to B. See, when T is greater than equal to B, the value of this function is 1 UBT and the value of UAT is also 1. So 1 minus 1, that will be 0 because you are subtracting. When T greater than B, the value of UAT is also 1, the value of UBT is also 1. We will discuss this part later. Now, T less than A. When T less than A, the value of UAT is 0 and UBT is also 0. So 0 minus 0, the value will be 0. Now between A to B. Between A to B, the value of UAT is 1. See, between A to B, when I am taking at equal to A, equality sign, the value of UAT is 1, but the value of UBT is 0. So 1 minus 0, it will become 1. So this is a pulse function. It is very important in understanding our Dirac-Delta function. Has important role in Dirac-Delta function. So this is a very important definition. Now, see second shifting theorem. This is the definition of pulse function. Second shifting theorem, most important. Let Laplace of ft equal to fs. S is greater than alpha. Alpha is the exponential order of ft. And a greater than equal to 0 be a real number. Then Laplace of ft minus a, see here, ft minus a, UAT. UAT is a unit step function which has discontinuity at equal to a. According to discontinuity, we have shifted here, ft minus a is equal to e to the power minus as Laplace of ft. See, this is ft minus a, but this is ft. Or you can write e to the power minus as into fs because I am taking Laplace of ft as fs. What is the proof of this function? This result? Let's see the proof. Laplace of any function. I told you Laplace of even Anurag. If Anurag is piecewise continuous and exponential order, then exists. If Laplace of any function, suppose you have any function is ht. I told you the Laplace of ht is 0 to infinity e to the power minus st ht dt. Then Laplace of ft minus a uat will be 0 to infinity e to the power minus st. Replace ht by ft minus a uat dt. And we know this function. This is a unit step function which has jump discontinuity at equal to a. Means this has value 0 when t less than a. This has value 1 when t greater than equal to a. So we have to break our integral at equal to a because the function, the entire function, if this function product of this function will not be continuous at equal to a. So we have to use the property of definite integration. 0 a to b fx dx equal to a to c fx dx plus c to b fx dx, where c is the point of discontinuity. So this can be written as e to the power minus st ft minus a into 0 dt because between 0 to a uat is 0, and from a to infinity e to the power minus st ft minus a, this value is 1 dt. So this is your 0 entirely. Now replace t minus a by b here. A is a fixed real number, so t will be the only variable, so dt will be equal to dv. What will be the change of limit? Change of limit. When t equal to a, lower limit of v will be 0. When t equal to infinity, it will be 0 to infinity, e to the power minus s. T, the value of t will be v plus a. F t minus a will become fv dv. Fv dv. So we are integrating with respect to v now, so remaining term will be treated as constant. So e to the power minus sa we can take outside, it will be 0 to infinity e to the power minus sv fv dv. So can anyone tell me what is this? 0 to infinity e to the power minus sv fv dv can be written as 0 to infinity e to the power minus st ft dt using first property, change of dummy variable. So this is nothing else Laplace of ft, or you can write e to the power minus as fs. So this is the proof of first shifting theorem. Second shifting theorem, sorry. First shifting theorem I have already studied. In lecture 1. You can go to the first lecture. We have studied first shifting theorem already. So now we have what we have. Laplace of ft minus a uat is equal to e to the power minus as fs, where fs is nothing else Laplace of ft and a is point of discontinuity. Now let's see some remarks. First, what will be the Laplace inverse of e to the power minus as fs? It will be ft minus a uat if we take the Laplace inverse. What will be the Laplace inverse of uat? Can anyone tell me what is the Laplace of unit step function? This is the important result. This can be written as 1 into uat. Okay, 1 into uat. Now compare with this result. What is your ft minus a? Ft minus a is 1, and it will be equal to ft also, because this function is a constant function. This function is a constant function. This function is a constant function. We can write like Laplace of ft. So it will be equal to e to the power minus as Laplace of ft means 1. I using this property here. Ft minus a, we compare ft minus a is 1, so ft will be also 1 because this is a constant function. And what is the Laplace of 1? I told you the Laplace of 1 is 1 over s. Laplace of 1 is 1 over s. It means Laplace of unit step function or Heaviside function ht minus a or Laplace of u of t minus a, same notation, is equal to e to the power minus a over s. If jump test continuity at t equal to a. If a equal to 0 means 0 is point of discontinuity. Point of discontinuity. Then what will be the Laplace of u0t or Laplace of ht or Laplace of ut? It will become 1 over s, because at a 0 it will become 1. I am using here this property for proving the Laplace of unit step function. Now let's see some more properties. Third remark. I told you the Laplace of ft minus a uat is equal to e to the power minus a Laplace of ft. Sometime we have to make ft minus a in ft, so better to make ft here. What we want to say? If we shift t minus a as ft, we are going to change in ft only, not any other term. So it will become uat. I have given the value t minus a by t, or t minus a some variable b here. So it will become e to the power minus a Laplace of ft plus a. I have shifted ft from t minus a to t. Shifted. Only ft I have shifted. So if we added a here, you can see we added a here, then it will become ft. So we have to add a here also. This is a Laplace of ft plus a. Remember, sometimes this property is useful and sometimes this property used. So you have to be careful which property I have to use. Okay. Let's see some example based on this results. Example: find Laplace transform of A. I am giving you A is f1t is equal to 0 when between it is 0 to 3 and t minus 3 is square when t is greater than equal to 3. Okay. Can we break in unit step function? See carefully. What is the point of discontinuity? 3 is point of discontinuity. So we have to write u3t. u3t. And what is the rest function? You have to keep this function here only, t minus 3 square. Now you can see that if t less than 3, this value will become 0, and ultimately product will become 0. When t greater than 3, this value become 1. So if you are interested in the Laplace of f1t, it is Laplace of t minus 3 whole square u3t. Not depend which result you are interested, but I will advise always use this result, ft into uat. This has little bit more calculation, but this will not confuse you. This is equal to e to the power minus a Laplace of ft plus a. This is very useful result in the finding of Laplace. And if you are going to find the Laplace inverse, then use first result. This is your second result when we shifted ft. Now if you compare, what is ft? Ft is t minus 3 whole square, and what is your a here? A is 3. If we compare with this function, so it will be equal to e to the power minus 3s, because a is 3, and Laplace of af of t plus 3. Are you getting my point? Because a is 3, if you use this result, e to the power minus 3s, because a is 3, and ft plus a, it means ft plus 3. So e to the power minus 3. If your ft is t minus 3 whole square, what will be the ft plus 3? It will be the t plus 3 minus 3 whole square. 3 is cancelled out, it will become nothing else t square. So it is Laplace of t square. And I told you the Laplace of t to the power n is gamma n plus 1 over s to the power n plus 1. So it is gamma 3 over s cube. Gamma 3 is factorial 2. So 2 e to the power minus 3 over s cube is the Laplace of the given. This is a very good example. We have one more example. Find Laplace transform of f2t equal to t square u3t. Now this is given in the unit step function, so very good. We can directly compare it. f2t is equal to Laplace of t square u3t. Use the second result I told you. ft into uat is equal to e to the power minus as Laplace of ft plus a. So if you compare it, you can see that if you compare with this result, your ft is t square, and what is your a is? Your a is 3. So this will equal to, now use this result, e to the power minus 3s Laplace of ft plus 3. So if your ft is t square, what will be the ft plus 3? Ft plus 3 will become t plus 3 whole square. So t plus 3 whole square can be written as t square plus 6t plus 9. Use the linear property of Laplace transformation. Laplace of t square plus 6 times Laplace of t plus Laplace of 9. It will become e to the power minus 3. As Laplace of t square is 2 over s cube, plus Laplace of t is 1 over s square. Laplace of 9 is 9 into 1 over s. So this is the Laplace of the given. But the second shifting theorem is basically used for the inverse Laplace transformation. So let's see most important examples I am going to discuss here. Find inverse Laplace transform of A, I am going to write here e to the power minus 3s over s plus 2. Write the shifting theorem. Laplace of ft minus auat is equal to e to the power minus as fs, or Laplace inverse of e to the power minus as fs equal to ft minus auat. In the finding Laplace inverse, you use this property. But for finding the Laplace, you use this property. ft uat is equal to e to the power minus as Laplace of ft plus a. So for Laplace, you use this property. For inverse, you use this property of second shifting theorem. This remark of second shifting theorem. So you have to find the Laplace inverse of e to the power minus 3s into 1 over s plus 2. Now we will compare it with Laplace inverse of e to the power minus as into fs. We will compare with this result. We can see that a is equal to 3 here and fs is equal to 1 over s plus 2. If you have fs, you can find ft. Laplace inverse of fs is ft, I told you. So the Laplace inverse of 1 over s plus 2 will become e to the power minus 2t. You can see my fourth lecture on the Laplace transformation. This is the Laplace inverse of e to the power minus 2t. This will become ft. Now, what is this result? This is equal to ft minus a uat. So it is equal to f of t minus 3, because a is 3, u3t. You have ft, that is e to the power minus 2t. What will be the ft minus 3? E to the power minus 2, t minus 3, u3t. So this is the Laplace. You can break an interval also. When t less than 3, this value will become 0. When t greater than 3, this value is 1. So into e to the power minus 2t plus 6 will be the Laplace inverse when t greater than or equal to 3. When t less than 3, it is 0. So what we have to do, firstly we will compare with this. We will find a and we will find fs. Then we will find ft using the Laplace inverse of fs, and we have to use ft minus a here. So if you have ft, you can find any value of f at any t minus a, t minus 2, t minus 5 at any value. Let's see one more example. Find the Laplace inverse of 4 into e to the power minus s pi by 2 over s square plus 16. So we will compare it again. Laplace inverse of e to the power minus as fs. What is your a here? A is your pi by 2 here. And what is your fs here? Fs is 4 over s square plus 16, can be written as 4 square. Now directly find Laplace inverse of fs. So Laplace inverse of 4 over s square plus 4 square is nothing else sine 4t. And we know that this is equal to, I'm going to write here, Laplace inverse of e to the power minus as fs is ft minus a uat. So Laplace inverse of e to the power minus s pi by 2 into 4 over s square plus 16 equal to f of t minus pi by 2, because a is pi by 2 here, u pi by 2t. What is your ft? Ft is your sine 4t. So ft minus pi by 2 will become t 4 times t minus pi by 2, u pi by 2t. If you multiply 4 inside, it will become sine 4t minus 2 pi u pi by 2t. Sine 360 minus theta, minus sine theta, and minus sine again will common, so it will be sine 40. You can simplify it in pi by 2. If you want, you can break also. It is sine 40 when t less than pi by 2, and it is 0. It is 0 when t less than pi by 2. When t greater than or equal to pi by 2, it is sine 40. This value is 0 because u pi by 2 will become 0. You can calculate it. This can be written in minus 2 pi minus 40. Now sine minus 360 minus theta is minus sine theta, so it will become sine 40. I am giving one example as your homework. Find the Laplace inverse of e to the power minus 2s over s square, e to the power minus 2s over s square, and I'm giving you answer also, it is t minus 2 t. Let's see Dirac-Delta function. This is a very important function, also important function. Dirac-Delta function. Let a function delta kt is defined as 0 when t less than 0, 1 over k when t is between 0 to k, and 0 when t is greater than k. So if you see the pulse function again, pulse function, I told you uat minus ubt. If you remember, I have discussed this. This is 0 when t less than 0. It is 1 when it is between a to b, and it is 0 when t greater than b. You can say this is 1 over k. So we can write 1 and multiply 1 over k. We can take outside. Or you will see that graphically it k is supposed here because k is positive. So we can draw this graph also if you are willing to draw. When t is between 0 to k, the value is 1 over k. The value is 1 over k. But at k, it is equality sign here. At k, it is becomes 0. So jump discontinuity. And up to t less than 0, the value is 0. So this is your jump discontinuity. So 2 points are jump discontinuity, t equal to 0 and t equal to k. Both are jump discontinuity. So if you see carefully, what we want to say here, if we take 1 over k outside, this will become 0 when t less than 0, 1 when it is between 0 to k, and it is 0 when t greater than equal to k. Now see again carefully. This can be written as by using this function. If we compare, a is 0 here and b is k here. So it will become u0t minus ukt. So this is your delta kt function, which is written in the form of pulse function. Or we can write delta kt is equal to 1 over k. This u0t is nothing else ut, I told you. This is equal to ht, and this can be written as h of t minus k. You can see ukt is u of t minus k or ht minus k. You can see the Heaviside function. So delta kt is 1 over k ht minus k. Now, if we define, what we define? Define delta t. This is actually Dirac-Delta function. It is a limiting case when k tending to 0 plus, because k is positive. Delta kt. So if k tending to 0 plus, when k tending to 0 plus, this value is tending to infinity, 1 over k. So what will be the definition of Dirac-Delta function? It is tending to plus infinity when t equal to 0. Because if k is tending to 0, it means 0. It means 0 less than 0. It means t equal to 0. And it is 0 when t is not equal to 0. Here t is not equal to 0. So this is the Dirac-Delta function. And this Dirac-Delta function has discontinuity at t equal to 0. If we want, we can shift this jump discontinuity at t equal to k. Jump discontinuity at t equal to 0. we can shift the jump discontinuity at any point as previously we did in the unit step function. If discontinuity at t equal to a, then what will be the delta kt minus a function? Similarly, we can write this will become 1 over k. Previously it was what? ht minus k, and we have shifted t from t to t minus a. So it will become ht minus a minus h of t minus a plus k. We can write like this. If you replace t by t minus a, because previously t equal to 0 means t. So this is your jump if delta kt function when jump discontinuity at t equal to a. Or you can write in the unit step function, this is the unit step function uat jump discontinuity at a and minus u of a plus k into t, the jump discontinuity at a plus k. If we take the Laplace both sides, so Laplace of delta kt minus a is equal to 1 over k Laplace of uat minus Laplace of u of a plus kt. See, I told you the Laplace of uat is e to the power minus as over s. So what will be here? It will be e to the power minus as over s minus e to the power minus a. Here you have s a plus k over s. Now simplify. You will get it is Laplace of delta k t minus a is equal to 1 e to the power minus as over s. We can take outside. This is 1 minus e to the power minus ks over s. Take limit k tending to 0 plus both side right hand limit. It will become to the delta function with jump discontinuity at t equal to a. So limit k tending to 0 plus e to the power minus as over s 1 minus e to the power minus ks over s over k. Sorry, here you have k. Here you have k. This is k limit. So e to the power minus as over as limit k tending to 0 plus 1 minus e to the power minus ks over k. As k tending to 0, this is 0 by 0 case. So we can apply the L'Hospital or expansion method here. It will become s into e to the power minus ks over 1 because you are differentiating with respect to k because k is variable limit here. Now if k is tending to 0 plus, it will become s, so it will give you the Laplace of Dirac-Delta function with a with discontinuity t equal to a is e to the power minus as. Now let's see some important results here. First, what we have studied till now? We have studied Laplace of delta t minus a is e to the power minus as. When a equal to 0, we have Laplace of delta t with discontinuity 0 is 1, or Laplace inverse of 1 is Dirac-Delta function with discontinuity t equal to 0. This is an important result. Similarly, we have two more results. If you see carefully, hk tending to 0, this is the differentiation of ut. This is the differentiation of ut or ht. It means because limit k tending to 0, it's a differentiability property. What we want to say here, the second result is the Dirac-Delta function is nothing else, it's a derivative of Heaviside function. Or if you have jump discontinuity at equal to a, it is h dash t minus. Now third result is, I have already told you, this is equal to u dash t also, because this is your unit step function, or delta t minus a is u dash t minus a. Now we have one more important property, filtering property of Dirac-Delta. So let ft be continuous and integrable in closed interval 0 to infinity open, then 0 to infinity, any function if you multiply with Dirac delta function delta t minus a dt will give you fa, will give you fa. This is a very important result. This function will give you fa, and a is point of discontinuity. So using the filtering property, we can derive some important result. What is the Laplace of delta t minus a? So by definition, it is 0 to infinity e to the power minus st delta t minus a dt. This is the definition of Laplace function. This function will come into the multiplication of e to the power minus st. Now if you compare with this filtering property, what is your ft here? Ft is your e to the power minus st. If you compare with this property, ft is e to the power minus st, and you want fa, it will become e to the power minus st. This is, I already told you, the Laplace of delta t minus a is e to the power minus st. That can be get by the filtering property within a line. When a is 0, it is delta t is 1, because a is 0. So e to the power 0 is 1. So this is another use of filtering property. So in the next lecture, we will study the solution of differential equation using Laplace transformation. And we will also study the differential equation which involve Dirac-Delta function or unit step function, which are very difficult to solve from basics of differential equation, but by Laplace you can solve very easily. Okay, thank you. This lecture is very important, so I advise you listen this lecture twice.